Testing, testing. Hi, everyone. Caw-caw! Caw-caw! Hey, did I mention this is at the Marietta campus? Just kidding. Just kidding. Hey, guys, I want to thank KSU and Parth and Greg for organizing this event and the students for attending the ITS Georgia monthly meeting. Thank you guys so much for being here. I'd also like to thank Utilicom for being our sponsor this month, and AFL for the flashlights that are actually really cool because they bend around corners in the center of our tables. I want to make a couple of announcements, and then I'll pass it over to a couple of people who are here who are being nominated for the board next year. They're just going to come up and do a couple of brief talks about why to vote for them. So just a reminder, you guys, the awards nominations are open right now. We currently have 0 nominations, so if we can push that, it is going to close a week after the annual meeting. Push that out to our companies and to our partners and to our cities, municipalities, and government for the award. It's really important. A lot of people put a lot of effort into this, so let's nominate some folks for these awards. Elections. Whoever wants to come up, you don't have to come up. You know who, there's 6 people who are up for nominations for the elections. I'm going to go ahead and open it up for you guys to come up and just give a quick blurb. Troy's going to go first. Go, Troy.
Hey, everybody, I'm Troy Galloway. I've recently moved to 360 and Nest about 4 or 5 months ago. So I've been in the ITS industry for about 13 years now, doing anything from SigOps to broadband to connected vehicles and everything like that. I've been on the board for the past 2 years, overlooking membership, helping with the annual conference, and also helping with the Southeast Summit that's coming up in 26. So if you guys want me to continue on for another 2 years, vote for me. Thank you. Bye.
Hey everyone, my name is Mary Thamati. You guys, most of you know me, but those who don't. I've been on a board member for the last 2 years. I've done a lot with the programs committee as well as the training. I've also helped out with the legislative committee. I've been involved in this industry for over 10 years now. Started off at the TMC, have done stuff at SigOps, and I've also done stuff with like the statewide traffic incident management. So just, and I've been really involved with ITS Georgia. Just really loved, all the different meetings and the committees and the technical stuff, and just really being able to bring kind of that learning and fun to ITS Georgia, and would like to continue to do that. So please vote for me as a board member. Thanks.
Hello everyone, my name is Gautam Mistry and I work for Arcadis. I have 20 plus years of experience with signal operations and ITS. I've been involved with ITS Georgia for probably 10 years now and have been on multiple committees. Recently, for the last 4 years, I've been on the technical committee and I chaired the technical committee last year. I love to work with people and love to bring new technology to the forefront with presentations and spread awareness. So I would love to do that with a new role. Hopefully you guys will nominate me or vote for me. Thank you.
Okay, thank you guys. There's 3 other candidates, Greg Ramsey, Kelly Patrick, and gosh almighty, there's one other one. Got him, who's the other one? Another awesome candidate, so thank you for that. It's been a day, sorry guys. Voting is gonna open up shortly after this meeting, so please, it's gonna be your primary rep who's gonna vote for the candidates for the next board, and it'll be announced, I think it's gonna be announced at the November meeting, not at the conference this year. Madison, do you wanna talk about the conference now that I brought that up? Okay.
Hey y'all, the conference is fast approaching. We're about 2 weeks away. We are totally at capacity this year, kind of an unprecedented situation. But just want everyone to keep that in mind. We cannot register anyone else, and just have expectations that we have a very full conference. It's gonna be a lot of fun. We have some really cool things planned and a great technical program lined up. So looking forward to seeing everyone, and let me know if you have any questions. Thanks.
Okay, that is all I have. You guys, I'm done for this meeting. I'm going to pass it to you. Thanks, Billy. I'm going to pass it to you, Utilicom. Christine Lewis is going to come up and say a quick blurb about Utilicom, but thank you guys for being this month's sponsor.
want me to have the mic? Okay. Okay, gotcha. I'm Christine Lewis. I'm the regional sales manager for AFL in the Southeast. Proud to be partnered with Utilicom Supply on the Georgia DOT broadband project, as well as others. I've recognized some faces here. AFL is we're a fiber optic cable manufacturer. I'm sure a lot of you probably are like, who's AFL? We're located just up 85 in South Carolina, but we manufacture fiber optic cable, fusion splicers, outside plant closures, all of that. The picture shown on the screen, those are items that some of our ITS partners have purchased through Utilicom. And most recently, we're super excited to be a part of the Georgia DOT broadband project, phase 1. New technology with a microduct and cable that's being jetted in. So if you're interested in taking a look at this, it's not your traditional installation method. Actually can install thousands of feet in minimal time by jetting cable in this microduct. So again, we're super excited to be partnered with Utilicom and appreciate your time here today. Thank you.
All right, we have 3 speakers today. Our first speaker is going to be Abraham Pizano. He's a first-year master's student in civil engineering, specializing in transportation systems engineering at Georgia Tech. His primary research interests include traffic operations, traffic engineering, traffic simulation, and multimodal transportation. In addition to his research, Abraham has been serving as the president of ITE Georgia Tech since 2023. He is also a registered EIT, and outside of work, Abraham enjoys collecting license plates, building Legos, and writing with fountain pens. Please join me in welcoming Abraham.
Hi, everybody. My name is Abraham, first-year master's student from Georgia Tech. As stated, a couple of my research interests have to do with traffic operations, but also by association, also a little bit of ITS. And today I'm going to be talking about a little bit of the data collection side on how we're changing the microsimulation calibration guidelines and how we're using drone and existing camera video. So, and this research was funded by GDOT. All right. So for those of you who don't know, what is microscopic simulation? So it's a traffic analysis tool, and what's really cool about this is that each car is modeled individually. So it's given its own set of behaviors, and it's given its own set of behaviors that include car following, and that has to do with the Weidman car following models that were developed a really, really long time ago, and also some lane changing, how vehicles are changing lanes, their accelerations while they're changing lanes. So there's those 2 things. And what's really cool about this is that it could be used to evaluate like system level impacts. So instead of looking at a single intersection, what about an entire corridor? What about a grid of intersections? So there's a picture of VISM on the right, and just showing a little bit of its capacities. So why use simulation instead of something like HCM or Synchro or some other traditional form of analysis? Well, first off, you don't always want to use simulation. It's a trade-off it's a balance between effort and detail. The more effort you put into this model, the more detail you're going to get. You're able to figure out underlying trends and other measures that you're not able to get all the time. For example, you're able to evaluate signalized corridors, seeing how both adaptive and coordinated systems are actually working. So you evaluate those signal timings. You could evaluate spillbacks. You could even do energy usage and emissions. Since energy usage and emission models are based off acceleration profiles of vehicles, you're able to extract that from the simulation and throw it into a model and then see what your emission and energy uses look like. The other cool thing about it is that a lot of these tools, like Synchro and HCM, they don't always consider multimodal evaluation. So in something like VISM, you could simulate bikes, you could simulate transit, you could have a train, you could have pedestrians, and you could see the impact of the entire system, and it gives you a holistic view of what's going on. So this is from FHWA, and it just goes over the model building process, which starts with planning, moves on to data collection and analysis, which I'm going to be talking about a lot. The base model development, so making sure we're building our model properly, error checking, because a good a model that has a lot of errors in it is pretty much rendered useless. Model calibration, which is the focus of the project that I've been working on, an alternative analysis, so changing up to see to evaluate different alternatives that have been come up in said study, and then a final report. So what is calibration and why is this important? So calibration has to do with the adjusting the underlying parameters of the simulation to most closely replicate local driving conditions. So for example, you're not going to see the same driving behavior in downtown Atlanta as in the middle of Nebraska. They're completely different, and a lot of its underlying parameters are impact capacities. So the capacity of two facilities in two different places might not be the same. So why do we calibrate? Well, like I said, traffic conditions change place to place and even locally, and drivers can adjust to different driving sites. So they might drive more aggressively somewhere where there's more congestion, for example. So we always want to replicate the local conditions. So this is just an overview of the framework that we're using to calibrate. So we have our real inputs and our simulated inputs, and then that goes into a simulated system and a real system, and then we have our outputs, and we compare our outputs, do some calibration and validation, and that's the general framework. So what exactly is the problem that we're looking for? So there's a couple problems with it. First, existing guidelines are pretty vague, and even state to state, they allow for, I think, too much engineering judgment, because how calibrating the model can be very, very critical. So if it's different place to place, we don't know if the process is actually working. So that's on the that's on the state DOT and the federal side, but also in research efforts, there's a lot of data that's going into, they're doing these things called black box approaches. So black box means we're inputting data into some system, and that it's spitting out a calibrated set of parameters, but we don't know what's going on. These like machine learning and AI and all that stuff, we don't know what's going on. So we need something that's transparent. We need something that we can know what's going on, so we have a better understanding of what's going on in the model. So how do we practically calibrate these models? So there's two key things. There's the calibration process itself, and then there's the data collection. Because usually data collection, when we think of data collection, we might think, oh, counting turning movement counts. But we're going to change that a little bit and start getting into vehicle trajectories and seeing like where vehicles are actually moving. So this is an overview of the calibration framework. So first we have our inputs, which include the field data, which I'll be talking about a little bit more. Our model itself, our objectives, a well-built model. We move that to our parameter calibration, which I'll be talking about a little bit more too. It's an iterative process, so we're using visuals so we could see what's actually happening in the model. And then we go through it a couple of times, we meet a stopping criteria, and then our calibration is complete. So just a little bit of an overview of the Wiedemann 74 model, and this is the corridor use model. So we have this thing called desired safety distance, and that's basically the headways between vehicles. So there's a static component to it, which is the average standstill distance, how closely are vehicles spaced together when they're not moving. And then there's a speed dependent component, and that has to do with two key parameters, bxadd, which is an additive form of the safety distance, and bxmult, which is the multiplicative part, as stated. So a little, just to give you an overview of the procedures, are proposed procedures. First is plotting the cumulative distribution functions, or CDFs, of the headways and compare them to the field data. One of the big things that these parameters do is that they move the headways. They move how closely vehicles are following each other. So we want to see, how do we get the model to replicate how closely vehicles are following. So once we have a baseline of our defaults and our field data, we start calibrating. We move our AX and BX parameters as needed, and then once we've gotten to a stopping point, then we look at the desired speed. So we look at what speeds are vehicles going at and how that distribution is shaped. We're not necessarily looking for free flow speeds, which is it's typically free flow speed and desired speed are used interchangeably, but we found that that's not necessarily true all the time. And because this is a complex system and there's a lot of elements interacting with each other, we find that an iterative process works a lot better versus saying we have free flow speed and we're going to use that as our speed, because all these parts of the system are always interacting. So, and on the right, it just gives the iterative process. So what about the data collection? So there's an existing infrastructure already. There's like the GDOT 511 cameras. There's CCTV cameras. There's cameras all over the place. Now, they're usually like on the right. They just show a picture. There's nothing to it. But there's potential to use this data to calibrate our models, and I'll talk about that a little bit more. The other thing is, what about drones? Drones, you could fly over a corridor and capture video, like hours and hours of video, and we know what's going on in the corridor. So applying this to a corridor model. So right now I'm working on a project that has to do with North Avenue and its calibration. So we flew 6 drones, and each drone captured about two hours of data, and we placed the drones in a way that's strategic to get all the critical components of our model. And applying it to the free model, we were successfully able to calibrate a freeway model using one of the 511 cameras. This was actually the camera that was being used. So we made sure to capture it at medium to high flow. So taking this, we could do this all over the state. So what about processing data? We have all this video, now what do we do with it? We've been using this cool tool called Data from Sky, and we're able to process the vehicle trajectories and see a lot of information about the vehicles that we wouldn't necessarily see otherwise if we just would have done counts. So what do we get from the software? We're able to get trajectories. With that, speeds, acceleration, position, and we're able to connect, to geolocate these videos. And so we know exactly where vehicles are at all times. We're also able to get headways, and we're also able to get turning movement counts. So we still get that. The other thing is we're able to classify vehicles. We're able to get if it's a pedestrian, if it's a car, if it's a bike, if it's a heavy vehicle, and that's just a sliver of what this software could do. So what else can we derive as far as calibration metrics? We could get departure headway distributions. We could get desired speed distribution. We could get lane change distributions. So we could get a lot of the underlying components of the system. So this is a picture provided from the software, and it just shows a little bit of what the software is capable of. And what we've been doing on this project is we've been doing a lot of things post-processing, but there's a potential to do this real time. It's a potential to hook up the software with the cameras that are already existing out there and being able to get several metrics. So here is a screenshot of the software showing each vehicle trajectories. So the blue and the green lines are the vehicle trajectories, and we could see where vehicles are taking turns. How are the vehicles actually using the infrastructure that's out there? Because sometimes driver behavior can be radical and like we don't know what's going on. But this gives us a nice visualization. We have the video, we see the trajectories, and we can make a lot from it. So a little bit until like the potential uses. So instead of doing these post-processing, we could do some real-time analytics. We could do operation measures. We could do flows. We could do volumes. We could do speeds. We could do energies and emissions. We could do things such as safety. We could look at how pedestrians, how bikes are using facilities. We could also do potentially like close misses and other safety metrics. There's also potential for digital twins, connecting the field data to a model and being able to get all sorts of metrics from that model. As far as like an ITS side, we could do adaptive signs. We could do adaptive signal control. This could be a tool that could be used for adaptive timing and all this stuff. And on the right, I have a picture of potentially how this would work. And a lot of it is like these emerging technologies that has to do with AI and machine learning. And this is just one part of it. So All right. Thank you for listening, and I'll be happy to take any questions.
Okay. Hey, Ben. My name's Kerry Lord. I work for 360 Network Solutions, and I want to introduce Ben because he works with me so closely on a project that we have at 360 Network Solutions. I'm also an alumni from Southern Polytechnic State University, which is now KSU. I did want to ask, like, how many students are in here? Oh, okay, it's quite a few. Okay, well, good. Well, Ben is a student here as well. He's studying cybersecurity. He started with us as an intern back in November, and now he's a full-time employee. Still goes to school, and he'll graduate next year. So he's, he's had amazing success on some of these projects. And so, I don't know, this industry, ITS, is civil engineers, software engineers, cybersecurity. So that's just so neat about it. So, I would encourage you students to network with some of these other professionals here and land something like that, okay? But I'm going to briefly show y'all this project that Ben is helping me out on. So this is the Georgia DOT Gwinnett Connected Vehicle Deployment Program. So it's a really cool project. It's putting OBUs, onboard units, on fire trucks, ambulances, transit, and then portable OBUs on DOT vehicles. So it's got a lot of innovative solutions. It's an open agency contract, 3-year contract with 2 one-year options. And Ben is very involved in it. He's gonna share the parts that he does. Just quickly, here's some of the major components for this project. So, it needs an OBU, which is on the far left. In the back there, that's called a router. So the router is able to take software updates over the air versus having to go back to the actual vehicle. In the middle there is called it's HMI. It's a tablet that's showing you, all kind of messages from the vehicle and from the roadside units. So it's talking to the infrastructure. And on the far right's the antenna. Now these are the 6 apps. The SPAT map at the top. SPAT stands for signal phasing and timing. Map will show you, it's a map of the area. So EVP stands for emergency vehicle preemption, transit signal priority, pedestrian presence alert, rail intersection blocked alert, and construction maintenance vehicle alert. So these are the apps that are applied on these OBUs for GDOT and Gwinnett County. And I'm going to hand it to you, Ben, but this is the architecture. So this was a major software development effort. Further developing MaxTime CV with Q3 and also with CAPS to be able to have a cloud and a system that could accommodate this. And Ben, you take over from here. Thank you so much. You're a great young man.
Thank you.
Y'all gonna love it.
So like Kiri said, I'm just going to be going over what I've been doing for the project since I started on it last November. I figured that it'd be good to give a bit of a high-level architecture, just a view for everybody, but mainly we're going to be focusing on MaxTime CV and CMCC. Basically, the way that the project works is you can see on the, I guess it's going to be on the left side of the screen, the OBUs. They send connected vehicle messages to the RSU. Those get forwarded into the controller. Controller handles the logic, changes the signal. Information gets pushed back up into CMCC. So first, I'll just give you guys a bit of a rundown of what CMCC is. This is going to be our connected vehicle application monitoring software. So what this does is it shows us live data of the lanes and the current signal phases that they're in. It also gives us information on the traveler information messages, the connected vehicle applications, and the onboard units, where they are and when they're driving through the intersection. MaxTime CV, this is where most of the configurations that I've been making in the last year have been. MaxTime CV is the software extension to MaxTime that's currently running on the traffic controllers for the county. It's going to be in charge of handling our SPAT, MAP, TSP, EVP, and TIM messages. It's accessible through the web browser. It's got a nice, pretty little interface to it, and The special thing about it is it does give us real-time data. So when we make configurations, we can see them pretty quickly whether or not they're going through the way that we want them to. So starting with programming the controller, this is where we get into what exactly I've been doing for the last year. So initially what you're gonna need is you're gonna need to form your intersection geometry. And if you see in the bottom right corner, that's a screenshot from CMCC. That's what your intersection geometry looks like. The way that we form that is we use the US Department of Transportation Connected Vehicles tool. What we do in that is there's a message encoder. So once we make the child map and we add all the phases along with the lanes and the way that they're supposed to be set up, we encode that message in an upper hex format. Plug that into max time CV, and it gives the intersection a map of what it's gonna look like. And that gets pushed up into CMCC, and that's how we get those purple lines that you're seeing up on the screen there. The next step after you get your map fully set up is we gotta put in these applications. So these are gonna be the rail intersection blocked, pedestrian alert, emergency vehicle, and construction maintenance. We do pull all of these messages from a template, so it makes it super easy to plug right into max time CV. Technically, the construction maintenance is formed dynamically, but we won't really get into that too much. So what you see on the bottom right-hand corner, this is actually the same intersection as the previous slide here, but now you got this big red circle around it. So what that's indicating is one of our TIMs are going through CMCC. What's cool about this is in the bottom left right here, this is max time CV's user program definition. So once I plugged in that TIM, I was able to go ahead and set it to always be on, and that allows us, this just goes back to max time CV being real time. I was able to plug that message in, set it to be flashing at all times, and immediately in CMCC it popped up, and I can tell that it's displaying the way it's supposed to and it's functioning correctly. So once we have all of our configurations set up, the next step in the process is to test it all. So what we're looking for here is ingress, which means is the controller giving messages to the OBU, and egress is the OBU pushing the information out to the controller. So for the ingress, the way that we test that is you see in the bottom right-hand image, we have the HMI, the tablet that's connected to the OBU via Bluetooth. That is the CAPTCH V2X Insight application that's open on that. So what we're looking for is that intersection geometry and that spat and map coming through on the tablet. That tells us that it's pulling that straight from the controller. Egress, the way that we verify that is after we've done our test run, we've gone through the intersections, we go and we check the signal request message and the basic safety message. If those messages are changing after we've driven through the intersection, that shows that it's getting pushed up, and it just basically confirms for us that communication is happening from both directions. So once we know that full functionality has been set up, our next step is to button up the rest of the intersections and really just make sure that the lanes are mapped the way that they're supposed to be. So I know I saw Chala here a little bit earlier. Thank you to him. He's been helping us out a lot with this, going through and comparing what we have in CMCC, the live data, to the original intersection drawings that were provided to us from the county. If we can confirm that the configurations that we've made in the controller are working, it's important that we also make sure that the lanes are set up correctly, so when a car comes through and it's granted preemption, that it not only just grants the message in general, but it does it to the correct lane. Again, this is just buttoning down the entire process and making sure that it's going to work the way that it's supposed to. And last but not least, I do want to give a thank you to all of our partners. I know I just mentioned Chala, but we have a lot of different partners that we've worked with. All of them have been very helpful and assisting me throughout this. This is my first time being on a project like this, and it was pretty hard at times. So thank you to everybody that helped us. I do want to give a special thank you to Dr. Kihei from ReachRF. He's been a bit of a mentor for me throughout this, not just giving me the answers to the questions I had, but also teaching me how to, figure things out for myself. He's been more than words can describe helpful to me. I also want to thank the county, Casey, Tyler, Ken, Daniel. Everybody's been so helpful to just responding and helping to do test runs and get RSUs back online and working, and just going for a project that is so technologically unique, and we're really blessed to be part of it. For the students here, I do want to say I'm just like you guys. I am still in school, and I'm sure that a lot of you guys are probably also looking for internships and to work in school. Just a little word to mind about that. It is very difficult to balance school and work at the same time, but the sense of accomplishment that you get from doing that is so valuable, and the confidence that you get in yourself knowing that you can work in this industry with these people, it's beyond valuable. I can't recommend it enough. I can't recommend this industry enough. And to 360, thank you guys so much for bringing me on, being part of the team. I've always felt since I started here like I'm part of the family, and I'm just grateful. I'm grateful to be part of this company, grateful to be part of this project, and I am grateful to be up here speaking to you guys. So thank you.
All right, our last speaker today is Chris Moultrie. He graduated with a bachelor. Oops, did I do? Oh, no, it's not. Y'all don't see that yet. He graduated with a Bachelor's of Science in Civil Engineering from Kennesaw State University in 2021. Go Owls! During this time at KSU, he developed a deep interest in traffic engineering through an internship with the Gwinnett County Department of Transportation. Following graduation, Chris joined AECOM and is an ITS traffic signal specialist, where he worked on the SigOps North contract, optimizing traffic flow at signalized intersections. Outside of his professional life, Chris enjoys exploring Georgia's hiking trails, cooking, playing video games, or watching others play them. He's also had a habit of frequently replacing the pack of golf balls lost during his previous round.
All right. Good afternoon, everyone. So this presentation is just going to entail some of the very basics of civil operations, where we are, and kind of what we do with some of the tools we have available to us. Then I'll jump into a demonstration of a live controller. So that said, I'll go ahead and get started here. Skip over that. And I'm going to explain what SigOps is. It's an abbreviation for signal operations. So essentially, it encompasses the entire state. We have six different regions, three in the metro Atlanta area, or the immediate metro Atlanta area, and then we've got three other regions outside of the metro region. I primarily work in the northern region, and in that region we have roughly 1,500 total signals communicating to GDOT's network. Of those 1,500, approximately 900 are maintained by SigOps or GDOT, and then total in the state, we have about 8,000 signals that are communicating to GDOT's network. Don't know the spread of each individual region, but about 8,000 total signals, both state and locally maintained, that are communicating to GDOT. So with that being said, we kind of briefly in my bio talked about optimizing traffic signal operations and optimizing traffic flow. And I'm going to give a brief spiel of kind of how we do that when some of the resources we have available to us, some of the tools that we use, as well as some of these tools are actually available to everyone here in the room. So you don't have to be a contractor, you don't have to work for the state to have access to some of these. So I'll share a couple of links at the end of this presentation, but essentially how are we doing this? How are we optimizing traffic signals and how we optimize performance? So cool thing is that majority of these signals are communicating to the GDOT's network. And because of that, we are able to collect data from them and store them onto data visualization sites, such as ATSPM, such as SigOps metrics. And by collecting that data, we're able to view data on that traffic signal to make better informed decisions. And we're able to pull those enumerations and decode them so that it is easily readable to just about everyone in this room. So we have that, but in addition to evaluating performance at traffic signals, we also have the ability to use GPS data, speed data, and they have an array of tools there. We have Google Maps, ClearGuide, Ridis, 511 also has real-time data on that as well. So we're able to pull that data there, and we're able to utilize not only traffic signal data that we are able to extract and view via ATSPM, but we also have GPS data that we're able to pull in, and we can view those speed metrics as well. And by being able to do that, we can optimize not only traffic or not only performance at an individual intersection, but if you have a cluster of signals along a coordinated system, you also have the ability to be able to analyze how vehicles are traveling through that corridor in any given direction. So we have the ability to do studies, before and after analysis, things like that. And this data is not only useful for conducting before and after analysis for your typical conditions, but we also can use this data to look at unforeseen circumstances. So say if there's an incident or if there's something that's unforeseen, unplanned, is what I like to call it, we have the ability to see that in real time as well. And because we have this speed/GPS data available to us through a multitude of sites, we are able to proactively alter signal timing at multiple signals at a time through ATMS software. ATMS stands for Advanced Traffic Management Systems. In this particular case, we're using MaxView through GDOT, and that allows us to change timings at multiple signals at a time. So say there's an incident on I-75 and we need to move traffic, traffic's detouring via Cobb Parkway or some other parallel route or viable detour route. We would be able to quickly implement commands on multiple signals at a time to be able to quickly and effectively manage those unforeseen instances. So those are just some of the data tools we have available to us. I'm going to go ahead and jump over to the controller demonstration so you can kind of see what that looks like and some of the key features there. So I will jump over here. And what I've got here is I've got an intersection. Essentially, what we have here is a live controller. This is all real time that's running, where we can see the status of a controller as well as the correlating intersection here. And for those who are not too familiar with signal timing, I'll just give a quick breakdown of what some of these things mean here. Can you see my cursor? You can. Okay, perfect. All right, so what we've got here is basically two rings. So ring and barrier basically allows phases to run concurrently and also ensures that movements that are conflicting with one another don't come on at the same time. So with that, you can see here we've got a ring and barrier here. Even number phases at a traditional intersection are going to be your through movements, and then odd number is going to be your left turn. So we've got that. And then we also are able to view how much time is remaining on each particular movement here. So we've got that, and then we've also have a array of valuable data here as well that we can look at just off the top here on this home page here. That allows us to see what's running, kind of what's going on. We have the status of each phase as it changes. We can see which phases have active vehicles in the detection zone. So if you look here, that's going to show you that that vehicle does have a call. So next time this revolves around here, and this next time this phase has the opportunity to come up, it's going to serve that phase if there's a vehicle here. And then we also have status of pedestrian movements as well here. So if a pedestrian presses one of these crosswalks here, you'll be able to see that there. Now, if you've driven along a corridor before where there are a bunch of signals that are running coordination with each other, you might have seen that, you know, sometimes we'll leave those walk indicators on to come on automatically. That's why you're seeing this here despite no pedestrian. So just thought I'd point that out. So that's the status page. Now, we also have the ability, if we needed to, for really emergency situations, because we have robust CCTV coverage, we have the ability to view all of this, view most intersections, and we can see if something's wrong pretty quickly. And if we needed to do something quickly remotely, we would be able to place a call on one of these. So if you see these boxes here, we have the ability to actually go in and manually place calls to controllers as well. So quite a bit of things you can do on this page. And some of the other things I want to touch on is, I mentioned ATSPM. I don't think I defined what the acronym means. That's going to be Automated Traffic Signal Performance Metrics. And like I said, that's the site where we're using all of the data from these controllers, and the data is being extracted, and it's being converted into readable charts that we can use to make decisions. So I'll just quickly go over where that is actually coming from here. So if I go to performance here, go to detailed event report, we actually have pretty much a list of just about everything that goes on at the controller. You're getting at least dozens of events a minute, and all of these data points are being decoded by ATSPM and converted into specific events. So we have all of this here that we're able to use, and this is going directly in ATSPM as our data points. And that's what we're using there to be able to view those charts. So we have that available to us. Now, for those not familiar with signal operations, you might be asking, how does a signal know when to change, what to run? So at a conventional setup, you usually will run your signal on a time of day schedule. You could do some other advanced cool things, but for the most part, we typically do run most of these on a schedule. And I'll just quickly show you how I know what this signal is running and why it's running what it's running. So we go to our scheduler here. We can actually, and I'll switch to tabular format here, you can actually see kind of the different types of events that we have here available for any given intersection. Depending on how sophisticated your timing is, you might want to do more or less, but for a signal that's running in coordination, runs a bunch of different cycle lengths, you typically want to program in some extra things here. So as you can see here, we've got our weekday, we've got our weekend, we've got holidays. So depending on what's running, or depending on what time of the day or what day of the week it is, what if there's a holiday, so on and so forth, we have that ability to adjust the timing there. And then from here, we've got our day plans here. We can actually view what's scheduled to run, when it's scheduled to run, when it's scheduled to change. So right now, it gives you which day plan is running, which is going to be our weekday. We can specify, what we want to run and when we want it to run. So that's what we have there. Something else I did not mention is the ability to view statuses. So I mentioned, and I'll just go back to my presentation here so we can cover that. I mentioned that we're using ATMS software, and it has the capability to implement, we have the capability to push out commands on multiple signals at once. But we also have the ability to view the statuses of these controllers. Not only are we trying to optimize signal performance, we're trying to ensure that the signals are operating as they're supposed to via maintenance. I mentioned we pull data from controllers into our data visualization sites, such as ATSPM, to view performance metrics on that signal. And that's reliant on functioning detection. So in order to proactively identify these issues, we do have ATSMS software that not only allows us to do commands, view statuses of signals in the timing perspective, but we also have the ability to look at it in from a maintenance perspective. Is it in flash? Is the detector not working? Et cetera. So ATMS software, very valuable, not just for timing, but also for identifying maintenance. And same with ATSPM. If your data is not reporting as you expect it to, that could indicate a maintenance issue. So just wanted to touch on that. So that was the demo of the controller. I do have one here, here on the table. Not sure if you can all see it here, but if anyone's interested, we can delve into that a little bit more, so you can kind of play around with it, see some of the different things that they can do. See what else we got here. So that's going to conclude the demo and the overview of signal operations. I did want to give you guys a couple of websites here that are actually accessible to everyone here in this room, to the public, where you can view, we have ATSPM, like I said, you can view signal information, and then we have 511, which allows you to view real-time data. It gives you a plethora of CCTVs. I think Abraham mentioned in his presentation that he was actually using some of the cameras from there. So we've got that available to you all in this room to look at it. So that's going to conclude the presentation. Thank you so much for listening, and thank you.
the drones you were using for the calibration on CCTV over North Ave. Did you use multiple kinds of drones or models? And then for the capability to have it up for 2 hours, did you experience any like issues with wind, or what were some kind of the issues, if any, you faced?
So for the drones, there was 6 different drones driven at the same time by 6 different pilots, and they had varying experience. I think there was a new guy, and and like he started recording like when the drone was on the ground, so we lost data there. But there was towards Midtown, there was a lot of problems with wind. But the good thing about the software we're using is that it tries to account for that parallax, that change in camera angle. So there's that. And also, the drones don't have a capability to record for 2 hours. So some drones had to come down at some times and then have to be swapped out with batteries and then have to be flown back up. But in aggregate, it was about 2 hours of data. So, yeah.
Any other questions? He's got.
I guess just a follow up to that, how long can a drone last on one battery?
I think it's 15 to 20 minutes. So they were DJI drones. I think I don't know the exact model, but I know there was multiple different drones. So, and they were all brought by like their said pilot. So.
Anything else? Do any of our students have any questions for our industry professionals in the room that you'd like to bring up? No pressure.
Okay, just kidding. You're not done with me yet. Thank you guys to our speakers and our sponsors today. Our next meeting is going to be the annual conference. Just a reminder that sponsorship is still open until September 6th. We're going to print that week, so there's still an opportunity to sponsor if you want. Just reach out to Madison. Our October monthly meeting is going to be back at a Wednesday, and it's going to be Jennifer Portanova with the NCDOT speaking about broadband update. Our sponsor for that is Atlas, and TBD on the location. We're still working on it, but we'll get it out there. But thank you guys so much, and travel safe back, and see you at the conference. Bye, guys.